Jensen Huang once said he loves constraints. This is a strange thing to hear from a tech leader. He leads a company that builds the future, but his words tell us something important. Limits can be a source of creativity. They shape ideas and force new thinking. But his words also reveal a hard truth today, March 11, 2026. The biggest ideas in AI are now meeting a very hard wall. This wall is not a theory. It is not abstract. It is a real physical problem inside a factory, a packaging problem. Known by a simple name, CoWoS-L, NVIDIA makes the most powerful AI chips in the world. The Blackwell series sells faster than anyone can imagine. Customers from every corner of the globe are placing massive orders. They want them now. They need them for their ambitions. Making these chips is not just carving silicon wafers. It is assembly at the edge of physics. At this final assembly step, the global AI revolution hits a bottleneck. CoWoS capacity is sold out, and the packaging wall stalls deployments worldwide. To understand the crisis, we must first understand the technology. CoWoS packaging is not a new idea. It has been used for years to build high-performance chips. The process allows a chip maker to place a powerful processor, or GPU, onto a silicon interposer. This interposer acts like a mini circuit board. Then, stacks of high-bandwidth memory are placed right next to the GPU on that same interposer. This proximity is the key. It allows an incredibly wide and fast connection between processor and memory. Think of it as a superhighway with hundreds of lanes. There is no traffic, just pure, fast energy. This chip-on-wafer-on-substrate technique enables the massive memory bandwidth AI models need. These models are vast, billions, sometimes trillions of parameters, demanding extreme data movement. Traditional designs with distant memory cannot keep up. CoWoS solves it by bringing components into one tightly integrated package. But as chips grew, they hit a barrier called the reticle limit, the maximum single die size. So designers embraced chiplets. Blackwell B200 uses two large compute chiplets side by side. Connecting them seamlessly requires CoWoS-L, the local silicon interconnect bridges that raise complexity and time. The Blackwell architecture represents a monumental leap in performance. It is the engine that everyone wants. Yet its power has become its constraint. Two massive compute chiplets push boundaries. They must communicate at a staggering 10 terabytes per second. LSI bridges inside CoWoS-L enable that bandwidth. Packing so much compute so close generates immense heat. That creates a hard thermal limit. The package must dissipate heat or the chip will fail. Early production saw yield-killing design issues. Engineers reportedly redesigned top routing metal layers. Fixes worked, but introduced delays and complexity. Beyond thermals, Blackwell hit a packaging limit. CoWoS-L capacity is extremely scarce. A gap opened between chips sold and chips shipped. The assembly line became the choke point, the packaging wall. Even with perfected design and soaring demand, the factory floor dictates the pace. Opportunity for rivals and a strategic dilemma for NVIDIA. A winning product they cannot produce fast enough. Hyperscalers need a reliable roadmap. The bottleneck forces an accelerated pivot, a new name and a new architecture. While the world struggles to get Blackwell chips, NVIDIA is already making a strategic pivot. The company is betting its future on the next generation, a platform named after Vera Rubin. Vera Rubin, the pioneering astronomer whose work revealed dark matter. The Rubin platform is not incremental. It rethinks the AI accelerator to break bottlenecks. At its core, Rubin GPUs built around HBM4, the successor to HBM3 and Blackwell. HBM4 doubles interface width and, with new controllers and tighter integration, nearly triples memory bandwidth versus Blackwell. That leap can change the economics of the largest AI models. It is a direct response to the packaging wall. More performance per package. Rubin GPUs pair with new Vera CPUs over 2nd-gen NVLink C2C for 1.8 TBps coherent bandwidth. Applications can treat LPDDR5X and HBM4 as a single coherent pool, NVIDIA claims a Vera Rubin rack delivers 5 times Blackwell's inference performance. If true, customers could hit targets with far fewer GPUs. NVIDIA says 1/4 the GPUs for MOE training. Fewer packages per outcome eases pressure on CoWoS lines. HBM4 supply is led by SK Hynix and Samsung. Expected majority to SK Hynix, excluding Micron for Rubin. Rubin packages 8 HBM4 stacks, 288 GB and 22 TBs per GPU. A Vera Rubin NVL72 rack, 3.6 exaflops NVFP4, 20.7 TB HBM4 delivering 1.6 PBS. This is the heart of the gamble. Do more with less. Not more factories, but smarter, denser systems. Success hinges on flawless Rubin execution and the timely arrival of HBM4. Demand for AI compute has entered an astonishing phase. We are no longer just building data centers. We are powering digital cities. The new unit of measure is the gigawatt, enough to power a large metropolis. Major companies now sign gigawatt-scale compute deals. This is the gigawatt war, a race for computational supremacy, and it raises the stakes for the entire supply chain. Thinking Machines Lab, led by former OpenAI executive Mira Murati, has committed to a gigawatt of NVIDIA-powered compute starting early next year. It is a multi-year partnership, with a significant NVIDIA investment and technical collaboration. A gigawatt commitment implies hundreds of thousands of accelerators. OpenAI and other hyperscalers are pre-booking future capacity for chips that barely exist yet. Massive orders let NVIDIA lock in supply, making scarce resources scarcer for others. You cannot power a gigawatt site with chips you cannot get. The bottlenecks urgency is laid bare. The struggle has become geopolitical. US export controls limit access to the most powerful AI chips. Rules target China's access to CoWoS-packaged accelerators. NVIDIA redesigns products to comply. A chip cleared 1 month may be restricted the next. Special reduced power variants add friction and delays. Lines are retooled midstream, compounding bottlenecks. A shadow supply chain can emerge, components and systems moving via less transparent networks. Uncertainty spreads. Global deployments must factor political risk. Geopolitics adds another layer to the packaging wall. Decisions in government halls now shape who gets limited CoWoS supply. All eyes on Taiwan, the choke point of advanced packaging. And Arizona builds, part of a broader de-risking push. The quest for sovereign compute turns allocation into statecraft, a managed market shaped by alliances. All roads lead to advanced packaging, the factory floor. TSMC is racing to expand CoWoS, the tightest link in the AI stack, from a 35,000 wafers month in late 2024 to a projected $130,000 by end 2026, nearly 4x. But new lines take 18 to 24 months to qualify. HBM4 also needs time. SK Hynix and Samsung must ramp aggressively. Construction, tool install, and process qual are the physical limits. Scarcity likely persists through 2026 and into 2027. NVIDIA is not waiting. It is cornering capacity. Analysts suggest NVIDIA is locking down 1,060% of global CoWoS demand through 2026. About 515,000 TSMC wafers earmarked for CoWoS-L, Rubin AI chips, Vera CPUs, Blackwell, and more. Pre-purchasing builds a fortress around its supply chain. Partners get flow, rivals may wait. This tightens the bottleneck for everyone else, consolidating leadership. Shipments could reach 5.4 million units in 2026, 2.4 million Rubin-based. The bottleneck becomes a strategic weapon. Controlling the pipe controls the market. Nations chase sovereign compute. Chips as strategic assets like energy and defense. Allocation is influenced by alliances, not just purchase orders. Jensen Huang's love of constraints meets the ultimate test. The Blackwell bottleneck showed the wall. Rubin offers a path over it. Factory expansion promises a wider gate. Later. But software's infinite ambition collides with hardware's finite reality. The stakes are immense, timelines uncertain, and the market racing toward a $1 trillion AI economy by 2030. Everything depends on delicate, microscopic assembly, in desperately short supply. As gigawatt deals mount and sovereign compute rises, one question remains: can the world's supply chain possibly keep up?